So first, I very much appreciate being able to share some of the insights that we've gained over the what I realize now is more than 15 years of shake table testing, and so oops, sorry. So I titled this perhaps the subtitle is even more accurate. It's really the challenges and opportunities that these types of tests provide us. And so today's presentation, I'm going to talk a little bit about where I see current status of building level systems research, where we should or could be going and why, and then obviously talk about academia industry collaborations in 2013, 2017. Again, the opportunities and challenges, and then four grand challenges that are all interrelated for buildings. And I'm going to talk about this in the context of wood systems, as you can probably guess, but again, these are applicable to all types of systems. So that's just the examples. So there's a National Academies report. This is actually the Gulf research program. So this is not so much, not as much related to earthquake engineering, but they basically have said a new kind of research is needed that can address the dynamic state of communities and their change in risk and resilience over time, can link information or data from disparate programs with each other into community resilience priorities, but ultimately to link research, data, and information with decision making. So I morphed that a little bit for buildings, and the first two are effectively the same, perhaps replacing resilience with functionality priorities, but it's really to ultimately link building research, data, and information with new design philosophies, innovative technologies, and then collective recovery goals. And I'll talk more about this collectivism within building research for communities. So I want to just touch on the stages of resilience. We generally in earthquake engineering we focus, at least over the last 50 years, we focused a lot on improving the hardening structures through retrofit and things like that. And with the goal of enabling quicker recovery. So for structural design, as I was preparing this slide, I had, well, structures are generally designed at the sub-assembly level. So we, for instance, in wood, we would design shear walls and then put them in the right locations, and the idea is that together they resist the extreme loading, and so it's implicitly providing that resistance or that seismic capacity. But there's these rare events, and as I was preparing this slide, I started to see that they're starting to not seem so rare anymore, a lot of these events, but they provide these dictate changes in and corrections to codified design, and we change the philosophy and we recalibrate over the decades or the years, but it does take time. And so modeling it at the system of systems level is becoming more and more accurate. And so, as Joel mentioned in his earlier presentation, a lot of the testing that we do is so that we can model. So the question then becomes, do we need to test whole buildings? And so again, then that, a few other questions then come to mind. How accurate are our nonlinear numerical models? So you can see me standing off to the right there under a big mass. And if that's a single degree of freedom model and I developed it and I'm sure of the ground motion, then yeah, I probably trust that response that I'm predicting. If it's 1,000 degrees of freedom or 10,000 degrees of freedom, and they're all interacting and you've tested some components, but not all of them, and you've not tested the system, do you trust it? Are you under the mass? So components and subassemblies also have different boundary conditions, like everyone out in the audience here knows, and they're difficult to enforce in space and time. We just had that question about, that great question about the rotational effects on the shake table, and those are things that have to be accounted for. And then system testing essentially can provide information on how to add these things in, the effects of retrofits, and then of course collapse simulation. And so essentially, the sum of the parts doesn't always equal the whole, and that's why we do these whole building tests, or at least that's why I've worked on them. So then we go up even a step further, the system of systems, and so recent disasters have revealed shortcomings in the design and the performance of individual facilities, but there's also a financial limit to how much funding can be put into these, and there's also private funding as well. And so a community is essentially a system of systems, and each building that we're modeling on the shake table is its own system of all these components. But then we put them all together, 10,000 or 100,000, to essentially form a community or a city. So one of the challenges, there's a number of them, but one of them is the existing systems, and that's the performance of buildings and how we can make cities resilient, building by building, as we're testing these, as we're doing research in this area. So this brings me to just an example of a large test program that we did. I was the final test and finale was a test program 4 months at the UC San Diego site. This was back when it was called NEES-Soft. I suppose it would be very soft we were doing. And so as many of you know, or especially if you're in the Bay Area, but many of these buildings, these particular types of buildings, these 4-story light frame buildings were designed, it says prior to 1970s, but it was actually, back in the 1940s, many of these. And so there was a CAPS program that looked at developing a inexpensive approach, relatively inexpensive approach that didn't disrupt the renters or the people living in these, and so they were bottom floor only or first story only. So this was a 5-story, or excuse me, a five university industry collaboration. It was primarily funded by NSF, but as I'll talk about in a little bit, a lot of times by the time we get to the this grand finale at the end of a multi-year project, there's not a lot of budget left to do a test, even if that was the idea. So the building, as I mentioned, it was we had different phases. I'll just run through them real quick. We had our construction phase. We were ready for testing. You can see the towers that you saw in past presentations for safety. We did a cross-laminated timber rocking wall retrofit, steel special moment retrofit, partnered with Simpson Strong Tie on that. And then a steel moment frame with wood structural panels, and that was a performance-based seismic retrofit. And that was really the purpose of the project, was developing that, as well as looking at the FEMA P807 retrofit accuracy or effects. And then viscous damping devices, and those were a partnership with Taylor Devices. And then collapse testing, and I'll talk a little more about that, and then recycling. So this was the team. You can see our 5 PIs. It's an outdoor shake table, so we all look much tanner than we did when we got there, as you can imagine. So bring your sunblock. And then Gary Mochizuki, Steve Pryor. I think I saw Steve on the call here today, or on the WebEx. So, and then we had 5 REUs. We were very fortunate, and it was a tremendous program. They did, a big bulk of the instrumentation. They worked, I think almost all of them wound up going to graduate school, if I recall. And then our 2 PhD students leading that, one from RPI and my student from Colorado State. So just a little bit to show you the construction. And so these are, like you heard from Tara and others, these are massive undertakings. These tasks, you're essentially building a real building, and so so just to show you a little bit of that. And then just when it's finished, you compare it to our existing buildings, and it's of course limited a little bit by the shake table size, the footprint, but the accurate you can get building ready for testing. Now, one of the unique things, and these are decisions that you have to make as you go through, was these buildings were built long enough, that so far back that there really wasn't any steel connection hardware available, and so it was essentially wooden nails. And so this was the only building I've ever tested where I put in a finished floor, had a finished floor put in, and that was because it actually provided stiffness and strength to transfer load throughout. So I want to jump to collapse testing. So we tested 4 retrofits, and those 4 retrofits were successful. They, the models were pretty good predictors, and so for this, we had about 350 channels of instrumentation, and removed 97% of that instrumentation, and you can see this occurring here. And so we had some what we call sacrificial instrumentation that stayed in the building. The collapse motion here, you can see, hopefully you can see my cursor, but so the collapse motion here, looking at the MCE, this was scaled at 1 to 1.8 G. The building period, when all the retrofits came out for this 4-story building, was actually almost at 1 second. So you can imagine how soft and how weak these buildings are. And so you're over here. And so it really doesn't look like there's much difference between the motions. But then we jump to the spectral displacement, and what you see is, again, it looks fairly similar. But what you notice is as the building softens, as it climbs from 1 to 2 seconds, then Superstition Hills, and many of you are likely familiar with that motion, has a massive ground displacement, and so we can see that here. So we chose that for the collapse motion test, and the main reason for that is from years of collaborating in Japan, one of the things that I learned, and many of us learned, from our collaborators there, is that the acceleration rarely collapses these types of buildings. It's really the displacement, and so it's essentially pulling the rug out from underneath the building. So here is the test. I've taken away the sound just because it causes some feedback on these presentations, unfortunately. But so you can see we're shaking with the Superstition Hills motion at scale to MCE. And you can see that bottom story extremely soft. There's 4 one-car garages down there. And remember, no retrofits in here. So our goal is to improve our models of collapse testing. And here you can see we're barely hanging on at almost 17% drift. And so same motion, and what you'll see is it never manages to come back to equilibrium. It tries, but and I always get a kick out of I think somebody in a car stops up here, if I recall. I think that was on the first one. Sorry, they stopped. I think they thought it was a real earthquake going on. And so if you on this tower right here, we had there was a camera. So I'll show you and so here we see this is that camera view. It's looking into, you can see the people down here watching in the distance, visitors. It was a media day. And we did have furniture in here, but unfortunately, it was a morning test, and so we just couldn't get the sun angle correct. So you can almost see that in there. And that was one of the sacrificial cameras that we had or used. So here's the aftermath, essentially, of the test. And so this helped us, significantly helped us improve our modeling. We also had a cross-laminated timber rocking walls. This was the first time that CLT had been tested. These types of rocking walls have been tested in the US, actually, I think anywhere in the world, for rocking walls on a shake table. And then I want to show a little bit more on the performance-based seismic design and retrofit. This was something we borrowed this logic from direct displacement design by Nigel Priestley in 1998. Andre Filiatro and Brian Foles improved upon it, and then for wood, and then Hang in the NEES-Wood project. I won't be talking about NEES-Wood today, but and then we took that design, that 6-story building in Japan, using that design approach and tested. But to that point, it couldn't really handle in-plane eccentricities and in-plane torsion. And so Bamani et al., as part of this project, NEES-Soft, improved upon that, and then that's what we used to do this design. So here you can see this is our partnership with Simpson Strong-Tie. They partnered on NEES-Wood, NEES-Soft. They'll be partnering on the 10-story test as well, as you'll see. So this was the big center of the building, intersecting shear walls and putting in continuous ATS rods. And here you see going through the floor. So we're pulling drywall out, working on this, a big stud pack being toe-nailed in. And here you see on the bottom floor, so remember this is taking this 2-bay frame is in the direction of the motion, and so and then right above here you can see the shear transfer from the frame into the diaphragm, and then above that is the stack of shear walls, that intersecting shear wall. And so just show a quick video. This was actually I think it's not quite the same quality as the other, but it'll get the point across, and you'll see a quick tour. It's very fast. This is, I think, Loma Prieta, and then the building was stiffened up enough, and so you can see a slight, quick kind of a surprising, actually, a second, almost a third mode, just in a 4-story building that quick. So, and then the lower frequency doesn't do a whole lot, so we'll jump ahead. So for NHERI Tallwood, you heard a little bit about this. There's you can see just a large number of partners on this, and this in this it's the idea is to develop and validate resilience-based seismic design, but also just to provide insight into how these buildings will perform. So this is actually the older project. This was the planning project from 2013 to 2015. And then moving on to this, and this is actually going to 2022 now. So this was the 10-story here. You can see the floor plan that'll align with the shake table size. There's been a 2-story test I'll show you, and this was kind of you could say it was a test of opportunity. I'll show you a little bit about that, and then testing at Lehigh as well. So this was the 2-story test. This was done in summer of 2017, and this had, let me show you this is a little bit better, you can see. And so here we see this is 2 shear walls, post-tension rocking walls. Here you can see the close-up, and she should start together. There we go. I think they're playing, yes. And this was coming back to the other question. This was actually Northridge at MCE level, run twice back to back. So the single degree of freedom accumulators handled that just fine. And that was because this is a resilient building. There was no damage observed. I'll show you the little bit that there was after 20 or so tests. And here you can see the motion. You can see the rocking. and then it just runs again, and then here, a little bit better view of the uplift. And this is just to kick back, just to avoid sliding, which we didn't have anyway. But and so this went up to about 5% drift. And if you look, this was the extent of the damage on the wall. And here's just an image of pulling the wall out. We're putting it in same approach. So the next step, as I mentioned, is this 10-story wood building test. It's essentially the first major shake table test designed that we're aware of, designed to minimize downtime. And so we're looking at very specific approaches with the various university as well as industry partners. And in doing that, we're developing time to functionality fragilities, which are allowing us to do this. And so I'll jump ahead just to talk about this before I run out of time. So for opportunities and challenges, I didn't show much related to NEES-Soft, but NEES-Soft was again a massive. It was a 14,000 square foot building that was tested, and so the early experiences in 2009, when we spent quite a bit of time in Japan, that one thing I noticed is for Japanese projects funded by the Japanese government, I don't think it's required, but there's always industry representatives at the table during the research discussions, starting at the very beginning. They're there, and it's because technology transfer is so critical and so important that it's a requirement for them to get funded. And so they bring industry partners to the table that early. Project teams for NSF proposals, I also think it's a great idea to include them as senior personnel, not necessarily paid unless they're a direct consultant. And then another thing I noticed is in Japan and here as well is ensuring that you give lead time for them to handle their intellectual property and preliminary patents and things like that if they need to do something. So you have to lay the timeline out early enough, because they know how long those things take. We don't always know that. And so that they can work with their colleagues to make sure that that's in place. And then what we've done is, whether it's formal or informal, we've always treated these things like cooperative agreements. In other words, making sure that they get something out of it. And of course, we get their expertise. Some experiences at UC San Diego in 2013 during NEES-Soft. One thing that, of course, it was apparent in Japan as well, but whole building testing is very expensive. So these partnerships are key to being able to even do it. I think Tara gave a presentation back in December, I think at the last workshop probably, and talked about the funding, percentages. And I didn't look at them, but I gave my breakdown. And as I mentioned earlier, the budget's often gone by the last year of these. And so, I would say at most, you have maybe 20% of whatever NSF, the NSF budget portion is maybe 20%. It could even be 10. If it's like NEES-Soft, it was probably 5% by the time we got there. And then 30%, just a guesstimate on the shake table use time. So that's something, it's money that you won't see pass through, but that's there. And then you have about 50% or more that you have to find. And so for a $2 million test, it's $1 million. So some experiences at UCSD in 2017. And so the PI of that project, I think I mentioned, is Shileng Pei at Colorado School of Mines. And he's also the same project that will be doing the 10-story test. He's the lead on this one. That was a test in 2017. It was a test of opportunity. And we were fortunate to partner with Steve and colleagues at Simpson Strong, Ty, and Hans Erik Blomgren at Katera as well as many others. The city of Springfield, Oregon was focusing on CLT, and the Tallwood Design Institute at Oregon State, or in Oregon, I should say, as well as many others. And so there was a host of groups that came together to get this test of opportunity done, and to really demonstrate that this was viable for a 10-story test. So on the upcoming 10-story test, and I think it'll span actually into a little bit of 2022 but this planning starts 2 years out. I think I heard Jose mention that it's 2 or 3 years in the making. Sometimes 5. You're thinking about it for 4 or 5 years, but then the direct planning, and this one we said 2 years. It might be closer to 3, to be honest. Now that I'm thinking of it. But fundraising is key. We're focusing, working with the Forest Products Lab, the U.S. Forest Service, international industry. We have colleagues in Japan. We'll be, talking to colleagues in Canada, where cross-laminated timber is even bigger than the U.S., or at least it was over the years. And again, partnering with Simpson, Kutera, KPFF, Home Structures, Sumamoto Forestry Corporation, and over in Japan. And then I just want to mention that there's the phases. We have a payload from Michigan Tech that was funded by NSF, and they'll be doing about a week's worth of testing, things like that. And so and then as was mentioned, there's 4 teams. So safety is key. There's 4 different teams doing comparative predictive analysis. We have one industry team, and one team in Japan, and 2 teams within the NSF portion of the funded portion of the project, all doing analysis and comparing and making sure that we can predict. Okay, so that brings me to kind of my, I guess you could say, my final comment here. There's 4 interrelated grand challenges as I see them, and that's the first one is really overarching. It's enabling collectivism in building design. And so, just as I mentioned earlier at the beginning of the presentation, we build a building, we design it with these components and put them together. A building should be designed with a community or a city's resilience in mind. What is it contributing to the recovery of a city? And then new codes and standards that are equitable and effective for recovery following these extreme events. And so balancing often some of the most impactful events aren't the most extreme. And then developing advanced technologies that are affordable for widespread use, and enabling incorporation and incentivization of technologies and concepts in US standards. And so finally, I want to close by just saying that one of the most rewarding experiences for me in the few projects that I've gotten to do at UC San Diego has always been to make sure I'm able to get out there, even as the PI, even though there's students and there's other people coming and going, but make sure and spend some time out there. Not because it's beautiful San Diego, but also because it's at least for me, it's been rewarding to be actually part of the details. And so just to give you an example, I want to thank all the staff at UC San Diego and researchers, but also to show you just the number of people that are involved in this type of testing. So these are just the people that were involved in that 2013 test. And with that, thank you.
This is Karosh. Thank you very, very much, Professor Van der Lindt. Wonderful presentation. There's one question in the Q&A, if it's okay. For multi-partner testing programs, is the researcher seeking out funding, or are the industry partners approaching the researchers? That is, who's pushing initially for the research? I would say that it's a combination. It can be either and or. So often, it has to be mutual. If industry is not going to work with you as a favor, of course, which of course we all know,
they they need something out of it. But that can range from some PR. It can range from being able to develop some of their own products, and that's why I mentioned the IP and the preliminary patent filings and things like that, because they may be able to use that as an opportunity to try some of their own things out. Many of them have their own labs and things like that, so they but they don't know, no one has a lab like this. So this is something that if you can sell the opportunity to them in a sense, and get buy-in, then that's ideal. And sometimes somebody from industry may not be directly contributing dollars, but they're contributing expertise, or they're contributing product that can allow you to save money, or to be more efficient and finish faster, because they know their products, they know their industry usually better than us. I hope that kind of answered it.
Thank you very much, John.